Hello, everyone. My name is Biao Shu from Central South University, China. I'm going to report the critical concerns of carbon dioxide in the reservoir of enhanced geothermal systems. From the ERA World Energy Outlook, so it predicts that the renewables are the fastest growing source of electricity generation during the 2018 to 2050 period. So from this right-hand side diagram, we can see it predicts that the renewables going to surpass power as the electricity generation in 2025, and is going to account half of the world electricity generation by 2050. So what are the renewable energies? There are solar, there are biomass, hydropower, wind, and of course, geothermal energy. So when we talk about geothermal energy, one of the most important part of geothermal energy is the hot dry rock. To mine the heat from the hot dry rock, we need to use the enhanced geothermal system, or EGS. So an EGS system is created by drilling a well into a hot dry rock body, and then you pump the high pressure water to create fractures or reopen the lateral fractures in the hot dry rock reservoir. Then those water you pump into from the injection well into the reservoir is going to be heated up by the rocks, hot dry rock. Then you're going to pump it out to the surface, to the ground surface, and convert the hot water into electricity by the geothermal power plant. So these are the EGS systems. So its power is based on the water. So you use water to create fractures. You use water to carry the heat from the rocks. So there are several disadvantages of water-based EGS, including the induced earthquake. For example, if you pump too much water, or if you pump it too fast, it's going to trigger those seismic events. And also, if you use water in the EGS, the water react with the reservoirs and result in major dissolution. And then you're going to precipitate in the pipes. And also, you're going to consume a lot of water in the reservoir stimulation and heat production period. And some of the water is going to last during this process. And in the reservoir stimulation, you always need to add some acids and other like additives in the stimulation water. And as those water lost, then you're going to have the groundwater polluted. So those are the disadvantages of water-based EGS. So to overcome these disadvantages, people proposed a lower EGS concept called CO2-based EGS. So by Brown in 2000. So it's to use supercritic CO2 for both reservoir stimulation and heat extraction. So Brown mentioned three significant advantages for the CO2 EGS. The first is to provide a very large buoyant drive, so significantly reduce the circulation pumping power requirement. Also reduce the scanning in the surface piping and other equipments, and also provide a higher thermodynamic efficiency. So our presentation is going to talk about many different aspects of CO2 in the EGS reservoir, including their physical properties in the reservoir stimulation, in the wearable flow and the heat exchange, and the geomechanical reaction with rocks, and also the CO2 geological sequestration. So first, let's talk about the physical properties of CO2 compared to H2O. So the carbon dioxide has a higher ratio of density to viscosity, and also great fluid mass flow rate and fluidity for a given driving force. Also, it has a higher compressibility and expansibility. And the CO2 as density changes much more than the water with the temperature and the pressure. So with all those physical properties, what is going to happen in the borehole flow? It shows that the use CO2 can generate great buoyancy drive between the injection wells and the production wells, which means it can reduce the external power required for the fluid circulation. Means you need less power to drive the CO2 circulation in the EGS reservoir. And how about in the reservoir stimulation? So this figures shows that from the left side figure, we can see if we use water as the stimulation fluid, you're going to create a single fracture. But if you use CO2, obviously you create many tiny, small, and fractures rather than one single fracture. So because the carbon dioxide has a lower viscosity, less surface tension, and a better liquidity, so it can easily get into the microcracks or voids of rocks. And so it can lower down the breakdown pressure, and to create more complex fracture layers and with coarser fracture surface. And how about in the heat exchange? So here are three figures. And the first one is the temperature, the second one, the heat extraction rate, and the third one is the pressure drop. So in these figures, the blue lines represent the water and the red lines represent the CO2. So in the first two figures, we can see that blue lines and red lines are quite close, means the temperature and heat extraction are quite close between CO2 and water. But in the third figure is the pressure drop. We can see that the red line is much lower than the blue line. So it means that if you want to extract the similar amount of heat, you're going to need a less pressure drop in the reservoir, in the CO2-based EGS than the water-based EGS. So you need less pressure to drive the CO2 than drive the water. And now we're going to talk about the geochemistry in the CO2 EGS. So this figure shows that there are three zones in the EGS, CO2 EGS reservoir. In the very center is zone 1. So in this zone, there's a single phase of pure supercritical CO2 and the anhydrous condition. So because the pre-existing water in this reservoir has been flushed out by the CO2 stream in the very early stage of the EGS. And so there's no more water in this zone anymore. They're only supercritical CO2. So right outside of the zone 1 is zone 2. So in this area, they're both CO2 and water. So it's a two-phase CO2 water mixture. And then outside of zone 2 is zone 3. In this zone is a single phase aqueous solution with the carbon dioxide dissolved in the water. So those the CO2, water, and rocks is going to have some chemical reactions. So the geochemical reactions of carbon dioxide with rocks, including the dissolution of primary minerals and the precipitation of secondary minerals. Those are the chemical reaction equations. So because of the chemical reactions between rocks and water and the CO2, so the unit axial compressive strength and Young's modulus decrease. And it decreases more if you have the supercritical CO2 in the water media. So, but keep in mind that the pure CO2 does not react with minerals unless there are water inside of the CO2, okay? And finally, we'll talk about the CO2 geological storage. From this diagram, we can see in the last 3 decades, the global CO2 emissions from the energy utilization increased, reaching approximately 33.3 billion tons in 2019. And so the geologic storage is like one of the methods to reduce global warming and climate change. So there are 4 different geologic formations are considered to be the best CO2 storage formations, including enhanced oil recovery in oil and gas reservoirs, and unmodifiable coal bed storage, and saline aquifers, and deep ocean storage. But in addition to these 4 formations, you find that there's the potential that to have the CO2 sequestration in EGAs. So like after supercritical CO2 injection into the hot dry rock reservoir, dissolve the CO2 causes the mineral dissolution and the precipitation in the outermost aquifer phase zone, which is the zone 3 we talked about previously. So result in CO2 dissolution and mineralization storage. The dissolution is a physical storage, but the mineralization storage is a chemical storage. So when you in the chemical storage, the CO2 fluid and rock interaction cause the calcite and the feldspar to dissolve and eventually to regenerate or accumulate. So which can fix CO2 into solid minerals. So CO2 sequestration in the chemical, the mineralization formation is very stable. So in summary, we talked about 6 different aspects of the carbon dioxide in the reservoir of EGAs. First, the physical properties, we talk about the higher expansibility and the compressibility, higher ratio of density to viscosity. And then the borehole flow is a great buoyancy drive between injection wells and the production wells, and reduce the external power required for fluid circulation. A reservoir stimulation lower breakdown pressure create more complex fracture networks with a coarser fracture surface. Heat exchange that with a similar heat extraction rate, but a smaller pressure drop. And geochemistry in EGAs, because the CO2 does not react with the minerals, so unless their water exists, so can reduce the mineral precipitation and reduce the possibility of pipe ecology and corrosion. And there's possibility to have the CO2 geological storage in the physical and the chemical way. And so these are the concerns of carbon dioxide in EGAs. So thanks for listening.